paper in Nature Communications in 2014. Absolutely beautiful data. He had a 200-gram single crystal of PMN 30PT, which is gargantuan by neutron scattering standards. He has already discussed the fact that he sees a local mode, these little peaks here, that seem to indicate a dispersionless excitation at high temperatures above Tc, which is roughly 400 Kelvin, but that when you cool down below Tc, in this case around room temperature, it develops a dispersion, so it delocalizes. That was the essence of this paper. And so the thing to remember is that the signal is weak. It's dispersionless above Tc, dispersive below Tc, and it is sharp in energy, so it indicates that it's some kind of a long-lived excitation. So my outline is as follows. For wave vectors near this wave vector here, 0.35, it's a little bit beyond the middle of the Brillouin zone, we will show that the weak peak identified as this local mode is actually real. Okay, it's real scattering, but we do not believe it to be an intrinsic phonon mode. Okay, it's not intrinsic to this system. We believe that this weak peak likely arises from a double scattering process involving a longitudinal acoustic mode. And then for other values of Q and temperature, okay, we suggest later on a possible model to explain the apparent temperature-dependent dispersion. Okay. So to start with, since I'm a neutron scatterer and I'll be showing a lot of neutron scattering data, I'll just indicate that the different ways of measuring the neutron scattering cross-section, S of Q and omega. If this is your phonon dispersion, this is your soft transverse optic mode, here's your acoustic mode. We do frequently constant energy scans. This is an ellipsoid that represents the instrumental resolution function, and you can scan that as a function of Q at a fixed energy, and you can get an indication of where your optic mode lives in Q. You can also scan as a function of constant Q and get an indication of where your phonon mode exists in energy. Okay? And it's this latter kind of scan that I'll be doing primarily. An example of that is shown here. This is on a compound that is nominally the same as the one that Mike Manley studied. These compositions should not be taken too literally. I've measured a whole host of PMN compositions. Typically, they're off by about 2%. Not too much, but they can vary a little bit. But this is close enough. And so it's the same nominal compound. It's not 200 grams, but it's fairly large. It was 80 grams. We measured these data on the same triple-axis spectrometer, BT7. And we did it under the same configuration, so roughly the same collimations and roughly the same same fixed final energy. So that way our resolution is comparable. And we note that we actually get the same relative intensities as Mike did in his data. So this is the local mode here that is situated between the acoustic mode and the optic mode. And this is at a wave vector of 0.3 reciprocal lattice units measured from the 200 Bragg peak. That's at all my data are at room temperature. Okay? And this is for a fixed final energy of 13.7. You'll see these numbers change a little bit during my talk, but these actually represent an important parameter that we can tune to try to test our results. So here's the wave vector we're at, and if I change it, so take a look. Boom. You see things change. The optic mode disperses. So does the acoustic mode. This is now a different wave vector. And also the local mode disperses. This is at room temperature where the mode is supposedly delocalized, as Mike indicated. So it does disperse with Q. For that reason, and the fact that he's also seen it in time of flight data, we believe the scattering is real. It's intrinsic to the crystal. It's not an instrumental artifact. Okay. Before I go on and talk about this local mode, though, you might have seen what's this split peak here. I've indicated with a question mark. So let me just show you then to explain that feature. Here is a very simple cartoon version of a triple-axis spectrometer. You have your reactor that you extract a beam of many wavelengths. It's incident on a monochromator. You select a single wavelength. This is the incident beam right here. That incident beam then impinges on your crystal, and you have scattering. It can be all sorts of scattering. For instance, the scattering can come this way where it's energy analyzed by another single crystal, and you could maybe measure a phonon or a magnon or whatever it is depending on your sample. But you can also have this situation of parasitic Bragg scattering. Parasitic Bragg scattering depletes the incident beam. You can measure that depletion by taking your detector here and moving it over here. And if you do, you get a little picture like this. So this is the transmitted intensity is a function of energy, okay? So as you're changing this monochromator angle, you scan your incident energy, which is what we did in these constant Q scans. And you can see there's a big dip around 5 MeV, or a little bit above 5 MeV. So how does that reflect itself in the data you're measuring? Well, that big dip is shown again here. That comes from the 200 Bragg peak, which is the single strongest Bragg peak in this crystal. And as you can see, that causes a little dimple. It takes a bite out of your acoustic mode, and you might think it was split, but it's in fact not. Okay? So parasitic Bragg scattering lives in these systems, and it's something to be aware of. You can also confirm that this is a spurious feature by changing the value of EF. Remember, that's the final neutron energy. It's essentially equivalent to changing wavelength. And you can also change Brillouin zones. So if you change from 13.7, where most of our measurements were made, to 14.7, it's a very, very small change. But you get a drastic change in the intensity. This now peak, it's very, very high. The dip is shifted. And if you change zones, say to 100, you see actually no splitting whatsoever. Now, one thing that's interesting is to note that the TA mode we measured in the 1KO zone here in blue is softer than it is in the 2K0 zone, okay? And you may wonder about that because if you have strong TA-TO mode coupling and you have a soft TO mode, you would expect that coupling to shift to the position of the acoustic mode, but it does not. It should do it in the 200 zone because the structure factor of the optic mode is strong. It should not do it in the 100 zone, where the structure factor of the optic mode is weak. Nonetheless, it happens. This was then the result of a paper by Chris Stock and Gen Shirani, who were discussing the Waterfall and other various series of TO and TA mode coupling theories. I don't have time to go into that very deeply, but basically, this was evidence of coupling to the diffuse scattering, which is dynamic at high temperatures. That was shown using neutron spin echo. So that's actually kind of important. It shows that there is coupling, but it's to the diffuse scattering, not to the optic phonon. And in fact, the fact that you have missing intensity here actually has implications for the data that Chris took. It actually strengthens his argument that this coupling is extremely weak in this system. So that's why we don't believe it's responsible for the waterfall effects. We don't agree with the Linka model. So coming back to this constant Q scan, you can perform a very standard test to see if a peak is real. All you do is change the wavelength, in this case, the fixed final energy E. Okay, and we did that. We made a small change. You can see that there is a small change in the optic mode from intensity. It actually has a slightly larger integrated intensity, but not much. You know, just a few tenths of a %. It gets a little broader and a little bit weaker here, and that's expected because your resolution volume is larger. The acoustic mode intensity is, you can see this follows very nice, the same shape here. It's again hard to tell what the absolute intensity is because of that parasitic Bragg scattering, but the thing to focus on is the local mode has shifted intensity by about 50% and position by about a quarter of an MeV. So again, the optic phonon shows a small intensity change, but the energy is essentially constant. The local mode changes statistically and significantly in both energy and intensity. For that reason, we don't believe this local mode is a true mode. Okay? This is a blow-up of that data that I just showed you. And here's the 13.7 data in blue and the 14.7 in red. And if I just collimate the vertical beam, now this is 13.7, both of them, but now I've just collimated vertically the incident and scattered beam, I can get it shift a different direction. So if I just go back and forth like that, you can see the effect is rather large. Okay? That should not happen with a real mode. All right. Now, there was a paper that appeared in Physics of B in 2004 by Henrik Renault and collaborators that explained a phenomenon like this in copper germanate, a magnetic system. And they extended the concept of double scattering and multiple scattering, which applies to elastic Bragg scattering, where you can get forbidden 1/2 order Bragg peaks, for instance, from double scattering processes, to the case where one of the scattering processes involves an inelastic cross-section, such as a phonon. Okay? And you might think, well, why is that? Well, in fact, for neutron scattering, you have larger divergences in a neutron spectrometer, and combined with the fact that these inelastic cross-sections have a large extent in Q and omega. They're not Bragg peaks. They're not delta functions in energy and Q. They're actually very big. makes it true that these inelastic multiple scattering conditions are very often, in fact, fulfilled. Okay. In fact, there are two types that this paper considers. One where you have parasitic Bragg scattering first and then followed by a phonon. So that parasitic Bragg scattering acts like a second monochromated incident beam that's tied to your crystal. And the other one is where you have phonon scattering first that then satisfies the Bragg condition, and you get this, again, a double scattering peak. Okay, we're going to consider the first case. Actually, this is not a new phenomenon. Bertram Brockhaus, who invented this triple axis technique, published a paper on lead in 1962. And it's perhaps not surprising that he would have observed this, because back in those days, they studied relatively simple systems like lead or aluminum. Okay, you can get big single crystals of those, right? Today, if you try to ask for a large single crystal of PZT from Zoyer, he'll have a fit. He's probably the only person that can do it, but it's not very easy. So today's systems tend to be more complicated. The case of PMN XPT is different because you can grow large single crystals. Brockhaus noted that he had two single crystals of lead. In one of them, he noted that this longitudinal mode here was not that well defined, but he got this parasitic, this double scattering peak that was transversely polarized in a longitudinally polarized scan. So he knew it was somewhat spurious. In a second crystal he had where this longitudinal mode was much sharper, indicating better crystal quality, this scattering was effectively absent. So his recommendation was that crystals that you study should be as perfect as possible, and that's not always possible. So just to go back to Renault's paper, to observe multiple scattering at some wave vector q, okay, with an energy E, there must exist a reciprocal space vector tau, and thus an intermediate wave vector km, and an excitation at q of the difference of q and tau with energy E. It's a lot of words, I understand, but here's the simple diagram. This is the one that you're familiar with. Here, this triangle here. This is the wave vector q. Here's the incident beam, and here's the scattered beam. But now you have an intermediate Bragg peak from parasitic scattering that then shifts your beam to now scatter from a totally different excitation. So you're transferring spectral weight from one part of the Bragg zone into another, okay, or vice versa. All right. So there are actually three relevant considerations for double scattering in this situation. Crystal size I've mentioned, crystal quality you see with Brockhaus, and in the case of PM and XPT, it is true that the crystals can be very, very good at sharp mosaic. But phonon line widths matter too, the intrinsic phonon line widths. So to sort of make that apparent, here's that scan again that I've been showing you, this constant Q scan. You see these modes here. Are they broad or are they narrow? Well, you have to compare to something. Let's compare to potassium tantalate. These are the same scans on the same spectrometer at the same temperature. Here we see that the modes here are very, very broad in comparison with those in an ordered perovskite like potassium tantalate. What that means is if you're taking a parasitic Bragg scattering process, your target is much bigger. Okay? You don't have to hit the peak right on the money. You've got a very broad peak. So that makes double scattering much more likely. Okay. So to follow with Renault then, he surmises that many, if not most, excitations measured in inelastic neutron scattering experiments are in fact affected by backfolding at the 1 to 5% level. And that local mode I showed you is about 3% of the optic mode intensity. And while that does not have any effect on extracted dispersions, it potentially could haunt detailed investigations. And again, this is another important comment he makes. Yet, unlike in diffraction, where multiple scattering involves infrequent coincidence, there is basically no energy that is clean for multiple scattering in large single crystals and neutron scattering. Being an effect within the sample, you'll see it on any instrument, triple axis or time of flight. Okay. So what I'm showing you here then are, in color, are the local mode intensities at high temperature, 600 in red, at 488 Kelvin here in green, and then when it's delocalized in blue at room temperature. That's the color scale here. What I'm showing in black are the values of the phonon intensities of PMN, the longitudinal acoustic mode, and the open circles, and then lead titanate. And what I was intrigued by, this is actually a comment that Chris Stock pointed out, is that at high Q, these values are all very similar. Okay? especially within the errors when you have such a weak peak. All right? So it's suggestive of a double scattering process where a longitudinal acoustic mode could be involved. Well, that requires a parasitic Bragg peak that is present and active during this relevant CQ scan, the constant Q scan that I've been showing you again and again and again. Okay, is that true? Well, here's that constant Q scan. I made it a little bit shorter. And we put a transmission scan on top of it, just like I showed you in my cartoon of the triple axis instrument. This is the 200 peak that takes a bite out of the acoustic mode. And looky here. We've got another parasitic Bragg peak process that's actually almost as strong. Note this curve goes up because the higher the neutron energy, the greater the transmission. So this is actually a large effect, and it's essentially right where the local mode lives. Well, what happens then, and that corresponds to 2 minus 4, 0. And if I form that difference, big Q minus tau, I get 0, 3.650. That's a purely polarized longitudinal mode. Okay. If I put in the 14.7 MeV transmission data, that's now in red, I see that this shifts a little bit to lower energy. Why is that relevant? Well, that explains his shift to the local mode. Remember, when I went to 14.7, it shifted to lower energy. Okay? So we think that's fairly damning evidence. Let's look at the longitudinal acoustic modes in this crystal. I wasn't able to reach 3.65, so I had to settle for 2.65. But what we see is all of these are very broad. There's spectral weight everywhere. Moreover, this guy has a peak right at 11.5, which is essentially the same as the local mode value. All right. So if this local mode is driven by an in-plane Bragg peak, and by in-plane I mean the L coordinate is 0, okay, so it lives completely within the scattering plane, then it should exhibit a Bragg-like dependence on the out-of-plane tilt angle. I have my scattering occurs in the two-dimensional plane, and I can tilt my spectrometer this way. And if I do that, I'll break the Bragg condition. It's fragile, right? The Bragg peak is a delta function. It wants to live in that plane. If you buck it up a bit, it's not going to work anymore. And that parasitic scattering acts like a second monochromated beam that lives with the crystal. So if I move it out, it's going to die, and so does my double scattering peak. So we took a series of data at a slightly different Q. This is 0.3, and we did tilt from 0 to 6. We see that this local mode dies. Now, Mike did provide an alternative explanation for that based on coupling of the PNR mode and the optic mode and so forth. But I think this is a far simpler explanation. And in fact, it's rather dramatic. This local mode dies exactly like the Bragg peak. It's not similar. It's essentially identical. Whereas these other modes, especially like the incoherent scattering or the acoustic mode, are all very, very slow and soft functions of tilt, which is what you'd expect a phonon mode to be like. All right. And again, this explains then why we see when we vertically collimate the incident scatter beam, we're effectively amplifying any in-plane process, right? We're no longer integrating out of plane. And so this local mode intensity, shown here, actually gets larger relative to the optic mode, which I scaled to be the same. So we see the relative intensities of the local mode has gotten larger compared to the optic mode. So that's all self-consistent. Okay, that's just what I said. And if you're still not convinced, then I have other data. This is the same data, only now at 14.7. Here's the local mode, according to the FIT. We took data at 8 MeV. There is a window at 8 MeV that you can use, and we don't see any local mode there. This is at the same Q, the same crystal, the same spectrometer, the same temperature, the same configurations, except now we've just changed EF. But now we have something else at a totally different energy. And I think I've figured out what that comes from. It comes from a totally different Bragg peak. Okay. So this really, we think, is damning evidence. If you think, well, what's going on here? This is just where the detector gets close to the incident beam. If I show you the FIT, where my optic intensity is, this is the FIT, you see that line there matches beautifully with the line here at 14.7. So there's no shift in the energy of my optic mode, which there shouldn't be by changing wavelength if it's an intrinsic mode. Okay. So Mike has raised some very, very compelling challenges to this picture, and he's right. There is no dispersion at high temperature, and this longitudinal mode certainly is dispersive. Well, the point is that there are many Bragg peaks involved. It's not just one. There's just an enormous number of them, and only a few are shown here. So here's the one I was telling you about before, 2 minus 4, 0. It comes up like this, but it touches base here, so you can get this sort of flat mode here. Here is 3 plus or minus 3, 1. So the two of them, it comes in like this. This can give you a flat mode here. And then the low temperature stuff can be fitted by something like 2 plus or minus 2, 2. These are all strong peaks. This one may be somewhat weaker, but there's still an outstanding question. You need to have some inelastic cross-section to scatter from. Otherwise, this doesn't work. So we say the waterfall effect is probably involved here because it is very strong. And it lives, here's 12 MeV data we took way back when. It lives in the right region of Q, and it is certainly temperature dependent. Strong, temperature dependent, and it has the right Q profile. So we believe that these other Bragg peaks can then give rise to that dispersionless feature at high temperature, and when the waterfall, the intensity settles down, then that then gives you more of this dispersive type behavior. Now, finally, the temperature dependence also, you might say, if I go back one slide, here doesn't really follow the extinction. Well, for one thing, it's not the 200 Bragg peak that's involved. That was the factor of 21 that Mike mentioned. This is 2 minus 40. The other thing is there's the phonon-Bose factor. That operates in the opposite direction as the release of extinction. Third is there's thermal expansion. Even if it's small, it changes this double scattering condition a lot. Okay? And any kind of change in the phonon line width, et cetera, also will change the intensities. So we don't have a very good understanding of how to calculate the absolute intensities of the double scattering. But just the argument of release of extinction does not invalidate this model. But there is a lot more work that needs to be done. So with that, I thank you for your attention, and I'm happy to answer questions.
Controversy, so we must have some questions.
Hey, Peter. So I just have kind of a general question. So, I mean, in the literature, there's hundreds of phonon dispersion curves from neutron studies. So, obviously, every single mode hasn't been studied to the degree that you've studied this. So, does this mean there could be many places where, there's misidentified modes?
Yes, I think so. And there have been papers coming out about that. I think Alexei Bosak, you had a paper on Xray scattering, didn't you, that identified exactly this problem. And I've had other colleagues that when they see this, they look at their Xray data and they go, crap, I better go back and double check that. It's not a huge effect, but if you have gargantuan crystals, then you really need to do some homework. And by no means, this is not obvious. I mean, Mike and Jeff Flynn and co-authors did an excellent job of trying to test this. And they still maintain that it's a valid mode. I don't think I've convinced them, because I haven't explained everything properly. But I think it's sufficiently compelling that it's worth having a conversation about this.
Another characteristic is below the ferroelectric temperature, the mode gets the dispersion. So how this is related to your interpretation?
Right. So that's, I think, the one we don't really fully understand, but as I was trying to motivate in this previous transparency, so you observe these blue dots. This is that dispersive part. So it tends to follow more this maybe the longitudinal mode. But there's also a giant cross-section here that's not shown, and that's this guy. This is the waterfall effect that Gen Shirani discovered way back when he was working with me on PMN and PZN and all these other compounds. All these relaxer compounds that Mike has studied have this effect, and they all have similar lattice constants. They all have broad modes, so I'm not surprised if you see them in all the crystals. Okay? But the temperature dependence is I think, complicated. Even Henrik Renaud in his paper said that the intensities are very difficult to calculate precisely. And these local modes actually are temperature dependent. I think Mike told me that they're actually somewhat higher at high temperatures, if I'm not mistaken. So this is a detail that I can't fully explain, but they do change with, sorry, I was going to say, he also mentioned electric field pulling wouldn't necessarily break the double scattering condition. Actually, it does change it because the Bragg peak's intensities change also. So there are lots of different things that can happen.
So have you tried to work it out for the time of flight condition? Because when you do time of flight, you have fixed EI. I mean, you know, and then EF is varying. So the Bragg conditions are all completely different when you're looking at the same points in Q. So how do they end up being in the same place?
So you did an EI of 25 MeV, right?
Yeah.
So, and you were doing EF fixed of 13.7 and your mode's at 11.5, so those two summed to roughly 25.
Yeah, but the Bragg condition is different. So because so if you're at a certain point in Q, if you calculate what is so all that matters in that case is just the angle of the crystal with respect to a fixed incident wave vector. So when you're doing the, you're varying EI. There you have fixed EI, and in the other one you have fixed EF and you're varying EI, and so you end up with it in a different place, and it has a different locus in Q space.
Sure. So the bottom line is I haven't looked at your time of flight data in detail, no.
I think you should continue the discussion in the break because it is some personal.
Okay. Thanks for your attention.
So thank you very much again. And the next talk will be given by Dr. Bozak, diffuse scattering in strontium barium niobate, 3 phases of
And then this is actually my pointer, but you just put it on Oh, you don't? Oh, okay. No problem.
Well, first of all, many thanks to the organizers for giving me this great occasion to be here and to share with you some nice results. Okay, the results we consider to be nice. I'm taking care about inelastic Xray scattering from phonons at the SRF. But today I will not show even single spectrum of inelastic scattering. This talk will be mainly concentrated on the diffuse scattering. Well, the reasons are data collection on synchrotron source is much faster than for an elastic experiment, and the pictures are much nicer. Then to make something useful from these pictures is a different story. So we played with a crystal of SBN with 60-40 ratio strontium barium. And well, I will give a really short overview, some description of our experiments, and then long description and discussion of our data with whole zoo of diffuse scattering and what can we extract from this data. Well, SBN is in some respect simpler than cubic relaxers of PMN type, but while structure is not simpler. Okay, it's uniaxial. So if you go from 3 dimensions to hopefully 1 dimension of interest, the life become simpler. Well, might be, but to describe the crystallography of this stuff, you have to go to 5D space because it's modulated structure with 2 extra dimensions needed to describe the modulations. So you see the literature data and how the structure was refined. The modulation was attributed mainly to the displacement of barium strontium shared positions along the channels, along bit channels. Well, and the structure was solved only at ambient conditions in polar phase. What happens in non-polar phase above the transition, nobody knows. Okay, once again, it's sometimes relaxer. If you go through the compositions, it can be well-defined relaxer for, say, 75%, or it could appear like normal ferroelectric, like for 40%. The composition we started was 60% or around something which you grow from congruent melt. Data on the studies of diffuse scattering with neutrons do exist, and that was a detailed study which shows that diffuse scattering contains phonon scattering, contains strong central peak scattering. There is quasi-elastic component about the transition, and there is no phonon softening associated to this transition. It was studied in the proximity of few nodes in reciprocal space located in HHL plane. What would be funny is to see what happens away from the explored territory. And the easy way, well, easy, fast, if you have access to synchrotron source, is to measure X-ray diffuse scattering, because that can be done literally in minutes. We did that study as a function of temperature at the bending magnet beam line with Dmitry Chernyshov, and then at ID23 macromolecular crystallography beam line, thanks to Sasha Popov. It's not macromolecular crystallography, but it's a very convenient setup for us. And then I complemented this data with some measurements on inelastic X-ray scattering. And the patterns we obtained are nice. Like in art, visual complexity is sometimes equated with beauty. And in science, complexity is often a pain. But, well, we tried to do something useful with this data. So here I put together a few cuts of reciprocal space at rather high temperature above the transition. And what we see here, Bragg reflections, thermal diffuse scattering, Huang scattering with size effect, incommensurate modulation with limited correlation length, so not Bragg, but some spots, something diffuse with Lorentzian shape, and something else diffuse with Lorentzian shape. So one by one, you see some representative cuts of reciprocal space for low temperature and for higher temperature. If at low temperature you see clear Braggs, what happens at higher temperature? You see something large, and I would not call that Bragg. And I'm not even sure that there is Bragg, properly speaking, component in this. By the way, if you go see these Braggs at low temperature, they do not fit P4BM space group. They don't fit B element. So, which puts some questions on the validity of published model of structure even at room temperature. Well, then, Huang scattering with size effect. However you represent it, you can call it butterfly, or you can call it differently. It's here, it's weakly dependent on temperature. And it's superposed with thermal diffuse scattering, and it's superposed in the same place with Lorentzian shaped diffuse scattering. So it's really big pain. Then, second component of nearly Bragg scattering, you see these spots in incommensurate positions, not Bragg peaks. Something rather narrow. I'm not sure if with home diffractometer you would interpret them as non-Bragg scattering. Well, it depends on the machine, obviously. And when you try to fit the shape, it appears to be squared Lorentzian, which corresponds to real space correlations somewhere around 10-15 nanometers, with only slight anisotropy. You see second order, and you don't see third order. Then something diffuse with Lorentzian shape, which I call B1, and something else diffuse with Lorentzian shape B2. Well, not a huge difference. So why I call them different components with the same shape? To distinguish them, we need a temperature dependence. And here you see representative intensity evolution taken for two different Q points on different beam lines. One family goes through the peak, another family goes to the plateau and stays at the plateau in this temperature range. Well, why the data sets are shifted? Because if you go to undulator beam line, be aware you can hit by your sample by a few tens of degrees. In this case, it was 40 degrees heating. And it's not the worst situation. For PMN, we had heating up to 100K. So you really have to take care about independent control of temperature. For example, to have phase transition really helps. So one family goes to the peak, another family goes to plateau, and if we take a larger range of temperatures, this plateau decays, but it stays quite constant for at least 100K, and then it decays slowly. So what happens beyond these 2 points? Okay, we have diffuse scattering maps. To take diffuse map, full 3D map, it takes a few minutes, so we could take a lot of temperatures, then make reconstructions, then plot them together. Here you see linear cats and their temperature evolution. So you see some peaks, they go to some clouds, they go to the peak and then decay, and some clouds, they go to plateau and they decay much, much slower. Okay, that was high symmetry direction. If we go low symmetry, we can just take plane of diffuse scattering, HK2 in this case, and then we stack as a function of temperature, and we see that in high symmetry directions, we have some clouds which go through the maximum and then they shrink again, some clouds which expand and they stay expanded. And if you go away to the inside of this construction, to low symmetry directions, to low symmetry peaks, you see that some of them, they do expand, they shrink slightly, but not to the initial diameter, which means that these peaks are somehow mixed. Well, to separate peaks with different intensity response manually, I'm too lazy, so I calculated some functions which do discriminate somehow semi-quantitatively these two cases. And on the bottom you see how they are recognized. Peak-like and plateau-like components. And two things. Then peak-like behavior of diffuse scattering is usually associated to strong Braggs. Plateau-like behavior is usually associated to weak Braggs or to forbidden Braggs. Some mixing is apparent, and if you collect, if you split these two families, you see that first family is mainly situated on unshifted mesh, and second one is situated on shifted mesh. Now I go to hand waving explanation. If you take centered lattice, 2D centered lattice, and you displace all the ions in the same direction, you create unshifted mesh, like on left-hand side and like what you have seen for B1 component. If you start to displace the ions in antiphase, which can remind antiferroelectricity, you will create shifted mesh. So something which reminds B2 component. And it looks like, okay, I oversimplify the picture, that B1 component is responsible for ferroelectric-like fluctuations, and B2 component is responsible for antiferroelectric-like contribution. Then something happens at the same transition temperature with third diffuse component, which is incommensurate modulation. Barium strontium shifts. So they don't just decay with temperature, but some of these peaks strongly couple to the diffuse scattering variation of a Lorentzian-like component. So all these three components are coupled. Well, funny enough, I could not find any clear statement about what ion is mainly responsible for ferroelectricity in SBN. That raises some questions, and probably I could not find the reply just because the structure of low temperature phase is more complex than reported, and structure of high temperature phase is just unknown. Already from comparing these two phases, one could extract useful information. We're actually working on that. We have few nice data sets, and I hope that they are nice enough to extract useful structural information. Then, incommensurate modulation corresponds to rather short range order with 10-15 nanometers correlation length. Does it fixed by chemical disorder? I don't know yet. There are three interacting components of diffuse scattering evolving with temperature, and two of them may be linked with competing ferroelectric antiferroelectric fluctuations. What is funny that antiferroelectric-like fluctuations, they appear at higher temperatures than ferroelectric-like fluctuations. In principle, it's not forbidden. But that means the structure of high temperature phase approaches the disordered state only asymptotically. In intermediate range, local order switches from ferroelectric-like to antiferroelectric-like, and only at much higher temperature decays to disordered state. So I think there is a lot of work to do here already with the available data. We need to improve our understanding of the system, and indeed once you start to look to diffuse scattering, you can find much more than you have expected. So the questions remaining: what is the structural signature of polar and non-polar transition? How B1 and B2 components will behave with the electric field? For instance, can we destroy antiferroelectric-like fluctuations by strong field in favor of ferroelectric order? Maybe we can shift phase boundary to higher temperatures. I don't know what will happen. It would be funny to try. And then how general our observations in SBN family? Well, and slightly beyond of SBN family, because these bronzes have many representatives which are rather promising and rather interesting. Well, thank you for your attention.
Thank you very much. Are there any questions or comments? Yeah.
Is there any possibility that the sample is twinned?
Twinned? It's certainly twinned in polar phase, but well, we can in principle pull the crystal and to see what happens. I don't think it's twinned in plane, but C-axis is for sure twinned up and down.
Any other comment? It's obviously not the case, so thanks again, and we come to the final, to the last talk in this early morning session, which will be given by Ilya Grünberg. Similarities between the structural dynamics and dielectric properties of perovskite oxides relaxer ferroelectric.
Okay. So I'm not Peter Gehring, so I would like to thank the organizers for inviting me to give this talk. And this was done with Hiroyuki Takanaka, Shulu, and Andy Rapp in University of Pennsylvania. And now I'm at, in a little bit was done at Bar-Ilan University, where I am right now. So I'd like to tell you about the similarities between these kind of very different systems at first glance, perovskite oxide relaxers and water. So most people here know a lot about relaxers, and I'll just very briefly go over the structure and the properties of them. So they're characterized by this diffuse phase transition, where the normally sharp ferroelectric to paraelectric transition peak is broadened, and it has, and of course, there's also dispersion and the dependence of the dielectric response on the frequency. And this is due to presence of a large number of cations. For example, for PMNPT, there's magnesium, niobium, titanium. And when we go to something which is titanium rich, then all this goes away and get something which looks much more like a normal ferroelectric. And there are three temperatures which characterize, three transition temperatures which characterize the structure. There's the Burns temperature, which is, let's say, around 500, 550, or 650 Kelvin, depending on the composition of PMNPT. There is this intermediate temperature T star, which was discovered about 10 years ago. And then there's a frozen temperature TF, or the freezing temperature TF, below which the dynamics of the material freeze, and there's supposedly not much going on. So that's the story. And for a long time, since 1983, this was described by, or explained by the polar nanoregion model. And essentially you have these kind of normal dipoles in normal disordered paraelectric state over here. And then when T burns, the relaxer phase appears, and this was characterized by Burns first, and then following him a lot of people use this, that you have these correlated regions of dipoles, which are kind of swimming in this non-polar matrix. And then as you go even further down in temperature, these small regions become much bigger, and they fill up the whole space and touch each other, and whatever space is not filled up by these polar nanoregions, you still have the polar, you have the non-polar matrix in between. So the two main features of this model, and that I'm going to talk about, is first of all, that polar nanoregions grow in size as you go from high temperature to low temperature, and secondly, that you have this non-polar matrix. So this is the model, and it has been questioned recently by several different works, experimentally, by the, for example, by the work of the previous speaker, and theoretically by us and others. And the question is, what exactly is the structure of relaxers? These are complex systems, and so it's very hard to know what exactly is going on, even mathematically to describe this, and also conceptually. And so to understand this, we did bond valence molecular dynamic simulations using pretty large systems. First we did 36 by 36 by 36 supercell, and recently we went to 72 by 72 by 72. So this is about 1.8 million atoms. And we can do this on nanosecond timescale, so we can get different dynamics. And hopefully, if we understand the local structure and dynamics, we can explain various mysterious features of relaxers. Okay, so the first thing, this was from 2013. We looked at the local order parameter for relaxer phase transitions, and we just took something very simple, which is the displacement magnitude of the lead in PMNPT. So this is the total displacement magnitude, and you can see that at high temperature and paraelectric phase, it's kind of rising very slowly. And at Burns temperature around 550, the rise becomes sharper, and then kind of plateaus, and sort of right over here at the freezing temperature. And we can decompose this total magnitude into static and dynamic components, and we see that the static component starts rising at T star, and at freezing temperature, the dynamic component peaks and then sort of rapidly drops. And so we can actually, just by looking at these very simple properties of the local lead displacement, we can see all the three transition temperature, Burns, T star, and freezing, and we get a pretty good agreement to the experiment. And this indicates that our simulations are pretty good, hopefully, and that they capture sort of the essential physics of relaxers. So then we go from the local picture, just looking at the individual site, to the non-local one, and now we look at the two different lead atoms and their displacements. So one over here, and we look at their angle. Okay, so the angular function, how much is the displacement correlated, which can use this angle to measure this question. And what we found was something pretty interesting, is that as we look at the dependence of this angle with distance, so this distance in angstroms, and 90 degrees means that there is no order, because this is a cosine, this is taken as a cosine of, or arc cosine of of 0, so R cosine of 0 is 90. So at high temperature, 700 to 600, there's absolutely no correlation. Everything's disordered from 0 all the way out to 150 angstroms, as you'd expect. But what happens is when you go to lower temperatures, there's always split between this sort of like a region of high correlation, where correlation grows very quickly as you cool down, let's say in this case to 200 Kelvin. But in this region, let's say here beyond, let's say 60 angstroms, the correlation is it's there. It's not 90 degrees over here. The angle is 60 degrees or 70 degrees, but it doesn't really change its temperature, whether we are at 400 Kelvin or whether we're at 200 Kelvin and 100 Kelvin also won't be around here. It's all the same. And this is unexpected because it goes against this idea that polar nanoregions grow. In this case, we see that there is no growth. The polar nanoregion or the region of correlation stays exactly the same at all temperatures. The only thing that happens is that the intensity of correlation increases as we go down in T. Okay? And we can think of it essentially that the system forms a high density of domains with domain walls, and just sort of how strong the ferroelectricity is inside each domain differs with temperature. And we believe that this high density of domain walls, and this pretty sort of small domain sizes, here about 6 nanometers, sometimes it's smaller, sometimes it's bigger. It's this high density of domain walls that gives rise to high piezoelectricity of relaxer ferroelectrics, because domain walls are very flexible and very responsive objects to electric field. Okay, so we can look at the snapshot of our simulation to get a visual picture of this. So here you have a dipoles at 300 Kelvin, and we can kind of draw these domains or these regions of ordered polarization. And we can see that if you go to 100 Kelvin, the domains, they look actually more or less the same size. Again, the size did not change, but the dipoles are bigger and they're more correlated. Okay, so then we can also look at the domain structure. So here I plot the polarization, Px, Py, and Pz. So Px is in black, Py is in red, and Pz is in green. And again, you can sort of go and this is just a slice through the simulation cell of 72 by 72 by 72 simulation, and we can see that there is definitely a change of polarization vector. You know, we start out over here in the 0 to 1 direction, then we go to 200 and 210, and then back to 0 to 1. And so there is this kind of presence of domains. Some domains are pretty big, some are very small. And the other thing that we can see is that there's polarization fluctuation inside the domain. That in a real sort of a ferroelectric, this will be completely flat, and there will be no variation at all. But here there's fluctuation, and again, this is even at 100 Kelvin. So this is not due to temperature effect. This is sort of like a static intrinsic effect of the relaxer material. Okay, so now we can look at the diffuse scattering, which is a very well-known technique for studying these kind of relaxer materials, and we can compare the diffuse scattering that we get to the diffuse scattering that experimentally is observed to validate our calculations and also to perhaps explain the origin of diffuse scattering. So here is data by Peter Gehring, this is for 10% at the titanate composition, and we have this butterfly shape around 100 and a rod shape around 110. So first we look at 36 by 36 by 36 calculations. So we have something which kind of maybe sort of looks like a butterfly, and it does appear only below the Burns temperature, and some which looks more or less like a rod, but again has some wiggles that perhaps not quite as nice looking as this experimental data. So we went to bigger size supercells, and we went actually about 8 times bigger. Again, this is like 1.8 million atoms. And now we see that the butterfly shape slowly grows in. The rod shape also becomes sort of smoother. And so we really think that it's the discrepancy between experiment and theory is mostly due to just unit cell size. And even at 72 by 72 by 72, there is, I think there is room to improve. But here we I think, capture the most the essential features of experiment. So we can look at our computational diffuse scattering as a function of temperature. So here at, again, in the ferroelectric phase, there is no diffuse scattering. You just have a Bragg spot over here, both in the 110 and 110 zones. And when we go to 500 Kelvin, we have appearance of diffuse scattering. And then as we go down in temperature, it changes shape more or less, I think, at T star and in TF. And this is in agreement with the experiment. And so now, how do I sort of conceptualize this? So I presented this before. We used this analogy proposed by Pirtz and Blint, where we basically say that the liquid is sort of like the ferroelectric phase, and the frozen ferroelectric phase is sort of like the solid. And the question is, what's relaxer phase? And we suggested that relaxer phase is basically water, or hydrogen bonded water. And this was first based on just a simple analogy between the dielectric response of PMN for PM and PT, shown over here, and water. And you can see that water exhibits this very similar relaxer-like behavior. It's just that the frequency range over here is in gigahertz as opposed to megahertz for PM and PT. And so it's sort of kind of, maybe perhaps simplistic, but you say, look, these dielectric responses are similar, so must be there's something similar collective local dynamics that are giving rise to this. And in case of water, it's a hydrogen bond network, and in the case of relaxer, it's a sort of like network of locally correlated dipoles, perhaps due to some sort of like covalent-like bonding mediated by oxygen atoms. So this was a hypothesis, and we used it to sort of present our model of relaxers. So first we have the ferroelectric phase, and everything's disordered here, very simple. And this is analogous to superheated water where there are no domains and there are no hydrogen bonds. And then we go to relaxer phase at Burns temperature. And now we see that you have these regions of ordered polarizations, but they're not static, they're dynamic. So this is two different time snapshots at two different times. So again, for disordered phase, there's nothing changes. Here, the positions of the correlated regions change. So there's a fluctuation in the position and orientation of the relaxer nanodomains. And that's at TB. And when we go to T star, so we have these, more or less the same size of these polar nanoregions, but now they're frozen in space. They can change a little bit. For example, here you see this one goes from being a little bit fat to being a little bit thinner, but more or less they're frozen where they are, but they can change the orientation of their polarization. So here, the location is static, but the orientation is still dynamic. And this is, we think, is sort of like it's like a slush kind of water. And then finally, in the frozen phase, you have everything freezes, at least on time scale of our simulations, and probably many experiments also, where you have both the positions and the polarization directions inside the domains are exactly the same at both snapshots. Okay, and so the main difference between this model and the old PNR model is that, first of all, the size of the polar nanoregions is fixed. There is no growth, or at least not a very significant one, as we go from high temperature to low temperature. And secondly, there is no nonpolar matrix. The dipole magnitudes everywhere are pretty large. So the question is, well, we have this sort of conceptual idea that water and relaxers are the same, but like, why is it like that? Is there some fundamental property that gives a similar dielectric response in both of these systems? Maybe it's just because they're both glassy systems, and we only have glassy systems, so we're going to have a glassy dielectric response, and really that's not really such a profound observation to make. So actually, last 2 years, people have started to notice this similarity, not just in the relaxer field, but also in the water field. I mean, I'm not an expert in water, but did some literature research, and so there was a paper in 2014 where again they looked at their new potential for water. This is a classic TIP4P potential. This is a new one that they came up with. Experiment, and again they see this kind of relaxer-like dielectric response. And they mentioned in their paper that this is probably because of some polar nanodomains that exist in water, just like they do in the relaxers. And this was also seen by this paper in 2015, where they looked at the electric constant contribution of a hydration nanoshell. So it's actually very microscopic. It's not a macroscopic, it's a microscopic contribution. And you see the same kind of relaxer-like behavior. Okay, so this is, again, just a dielectric response. And I guess it confirms a little bit that we're not barking up the wrong tree. But what about structure? So the first thing we can look at is a simple order parameter, very local order parameter over here that we found for the relaxer transitions, and that's the displacement magnitude of lead inside its O12 cage. And we can compare it to the data that people obtained in 1997 for the chemical shift of water. So chemical shift of water, 1H chemical shift, is proportional to the number of hydrogen bonds. That has been shown by MD simulations, and I think by experiment also. And in this paper, they looked at it at a very wide temperature range. They were only able to do this, of course, because they doing water in 250 bars at high pressure. Otherwise, of course, there is no such thing as water at higher than 100 degrees Celsius. And what they see is that quite a similar dependence of this chemical shift, which is the number of hydrogen bonds or local order parameter, as what we found in our displacement of the lead atom. So again, we have a slow rise at higher than a certain temperature. Let's call it T Burns, and then it starts increasing rapidly, and then once around this T star or TF kind of starts to plateau. All right, so this is a similarity, and seems to indicate that similar effects are going on in water and relaxers. So again, this is local. What about the non-local? So here is again our picture of where we see that the change is localized in this 60 angstroms or 6 nanometer region. And so this is a paper by Zhang and Gali, also very recent, where they looked at the longitudinal dipole-dipole correlation function using MD simulations. Okay, and what they see is that past this 15 angstrom or 1.5 nanometer cutoff, whatever temperature or pressure you use in the simulation, you get exactly the same dipole-dipole correlation function. The change happens over here. And actually, so say this, that you have this nanodomains of about 1.5 nanometer radius, and they're nearly independent of temperature and density between 240 and 400 Kelvin. Okay, so this is very similar to what we see over here. And taking a look inside this domain, which is, this is the domain of fixed size, we can look at some other data from not from the Gali group, but from a different one. So first of all, we can look over here on the right side. This is from MD simulations by Kumar et al. In 2013. And this is a shorter distance from 0.2 nanometers to 1. In other words, inside 10 angstrom radius. And from 230 Kelvin to 300 Kelvin. And you can see that the changes are similar to what we observed before, that as the temperature goes down, the correlation goes up. And then but the effect becomes weaker with increasing distance and kind of dies out over here at this let's say 1.5 nanometers. And this is the correlation function that they had for the dipoles, but you can also see this in a very basic pair distribution function for water, which is sort of the most fundamental property that people have used to characterize the water structure. So these are very high resolution measurements published in 2011 and compared to TIP4P simulations. And so what they show is that, again, for this region of, let's say, 1.2 nanometers, 12 angstroms, there are changes with temperature, let's say, from 7 Celsius to 66 Celsius, but they're all localized inside this region. Once you go past the 4th, maybe the 5th hydration shell of water, then the structure does not change. Inside, it changes a lot with the sharper and sort of more pronounced peaks, indicating more correlation at lower temperatures. Okay, so we see that correlation and order inside these fixed size polar nanoregions rise in both PMN PT and in water. And so that's my conclusion, that the signature of these local distortions in relaxers is this formation of multiple domains, which are pretty small, and the size of these domains does not change when we lower the temperature. There is no nonpolar matrix as far as we can see. Maybe you can think of the domain wall region as a nonpolar matrix, but I think it's not such a good picture. It's much more of a domain wall issue. This high density of domain walls gives rise to piezoelectric response, and usually high piezoelectric response. And again, we see that these are two similar glassy systems, water and relaxers. And I believe that this is not a sort of a general feature, but it comes from the same structure of these local fixed size correlated polarization nanodomains, which do not get bigger as you lower the temperature, but just get more correlated. And I'd like to acknowledge funding sources, and thank you for listening.
Thank you very much. Are there any questions or comments?
Regarding the dielectric dispersions of water,
Yes.
it's a very common nature of the glass-forming liquid.
Can you say this again?
It's a very common nature of the glass-forming liquid, such as
Yes.
alcohol
Yes.
or
I mean,
sugars.
Yes.
But in this case, even if you apply fields, no polarization appears. It's a structural glass phase is completely different of PMN.
Can you repeat the question?
Yeah. Regarding the glass-forming
Yes.
liquid, even if you apply field, polarization never appears. And also, glass-forming liquid, there is no first-order Raman scattering. However, the PMN above TC, strong first-order scattering appears by the symmetry breaking.
There's no polarization appearing in the hydrogen bonded system.
And there's no polarization microscopically, but locally there are, they can have correlated regions which are polarized. And that's the first of all. And secondly, I think it's not necessarily an exact analogy that you have these polar nanodomains. I mean, the people who did MD simulations for water, they say that there are these polar nanodomains. But it could be just a question of order, right? They just you have an ordered, very, very locally small size region of order which is embedded in this disorder. But I think it actually is polarized, again, on small scale. Just like in the relaxers, there's polarization on small scale, but if you look at the microscopic scale, there is no polarization.
Any other comment? Are there any other comments or questions? Ah, yeah, very far in the back.
Yes, could you explain the butterfly shapes of the diffuse scattering directly in terms of the structure?
So we think it has to do with this multi-domain structure. I didn't show this before, but we tried to model it sort of simple models where we have, let's say, 180-degree domain walls or 90-degree domain walls or no domain walls, just and nothing really fits except when you have this kind of we did 71-degree domain walls. Maybe other ones will work also, but the message that we got, and again, this is actually an area that we have to do a little bit more work on, is that you have to have a multi-domain state of certain kind of domain wall orientation to get this diffuse scattering butterfly shape. Otherwise, you will not get it.
Okay. Any more questions? Seems to be not the case, so I thank all speakers of this session. And the coffee break is open.
正是跟齐宇博说，你说在那个上那个 App 上看到你了，就是怎么没见到你呢？昨天。
我昨天没来。
哦。怎么样呢？
What's the definition of D sub INSD distance of INSD? Your analysis. You measure the distance.
You are the first speaker.
I am first speaker.
I am the second speaker.
Okay. How did you try?
So instantaneous is the simplest one because it's just if you look at the position of the oxygen center, and if you look at the position of the lead atom, and you take the difference, that's it.
Yeah. Okay, I see. So,
yes.
So it's, okay. Whether there is that polarization or not. So.
Instantaneous. The static one is a little harder. The static is if you just the one that doesn't change on the time scale.
I see. Okay. So, what's the Hamiltonian? Because you didn't show.
So the Hamiltonian is bond valence model. It's an atomistic potential. I can show it if you want.
We have to bring our computer.
I can show it because I only have 1 minute.
Yeah.
Not such an interesting thing.
You connect now. Okay. HDMI. What?
Is this bigger than it was? I feel like the screen is quite a lot bigger than it was.
It's enough.
It's a very simple. We need for 8 like 11 volts.
It's me.
I will use probably this one. I will see which one is better.
I'll just leave that there.
This is